All right, and we're continuing to talk about the number theory that we need to know to understand public key cryptography. So let's go to the drawing program. Zernal. Here it is. Okay, does that look okay to everybody?
Yeah.
Okay, good. So last time we talked about GCD, and we spent most of the time yesterday saying that GCD AB is the same thing as GCD of B and A minus B, which is the same thing as GCD of B, A mod B. And this gives us a really fast way to compute GCD, and we actually did it as a Python program last time. You know, it's just basically, you can, how could you do it in C? You just say, if B, I think, is equal to 0, then return A. That's because everything is a divisor of 0, so the biggest common divisor of 0 and A is got to be A, because A is a divisor of 0 and itself, and it's bigger than 0.
Like a base case.
Yeah, that's the base case, and otherwise you return the GCD of B and A mod B. And so what did we just define here? This is GCD of A and B. So this is a very efficient algorithm. It's called Euclid's algorithm, and it runs in time proportional to the number of digits in A and B. So even if you have inputs that are thousands of digits long, that means that this thing only runs in thousands of steps, which a computer can do in the snap of your fingers. Okay, so I want to give like an example, and after I write it all down, we're going to go back through and smarten it up a little bit and explain the extended Euclidean algorithm, which I think everybody has already seen before. So the idea of the extended Euclidean algorithm is if D is equal to the GCD of A and B, then there's some way to write D as a linear combination of A and B. So D can be written as S times A plus T times B for some integers S and T. And this is a very important fact. This is basically the secret to doing modular exponentiation, modular inverses. And
that's true for like all numbers, pretty much.
For
right?
all numbers A and
or
B.
prime numbers.
For all numbers A and B. For all numbers A and B, if you take their GCD, there's some way to write the GCD as a linear combination of the two numbers. And in fact, it's the lowest positive number that can be expressed as a linear combination of A and B. So, you know, one way to understand the GCD and in terms of geometry is it's like the smallest common measure. So if this is A and this is B, and you imagine them being made up of blocks, kind of. So maybe 1, 2, 3, 4, 5. 5 is not very good for GCD. Let's put 6 there. And let's say that there are 8 blocks here for 8. 1, 2, 3, 4, 5, 6, 7, 8. So the geometric meaning of GCD is like the least common measure. So if here you have 8 blocks and here you have 6. I don't know why I'm writing B. 6. So what is the GCD of 8 and 6? 2.
2.
Yeah, so that means the greatest common measure is 2. So that means that I can express this as a bunch of 2's. And I can also express this as a bunch of 2's. So I can express this as a bunch of doubles. Except I'm messing it up somehow. 1, 2, 3, 4,
There's
5,
9.
6, 7, 8, 9. Oh, okay. Thank you. So I put too many boxes there. Okay, so GCD is like the least common, the greatest common measure. And there's always a way to express the greatest common measure as some kind of combination of the two. Like for here, it would just be A minus B equals 2. So that would be a simple example. In other cases, you might need to sort of double this stack and quadruple this stack or whatever to make the difference between the two stacks exactly equal the common measure. But you can do it. Okay. And it's the smallest number that can be expressed as this linear combination too. Yeah, baby. Sorry, I think my daughter just came back in from playing outside. It's a really nice day. So let's do all this with two numbers. Let's find the GCD of 346 and 82. So I'm going to do this in kind of a systematic way so that we're going to turn it into our explanation of the extended Euclidean algorithm too. So the first thing I will say is that 346 is equal to some number times 82 plus some remainder. So what goes in these slots? What goes there? Maybe it's not obvious.
Coefficient and the return and the remainder.
Yeah, this exactly. So this is like the number of times 82 goes evenly into 346, which is 4.
4 times, yeah.
And this is the remainder, which is, it turns out to be 18. Okay. Now, if you think of these things as being A and B, this is A mod B. Okay. So now we shift things over by 1, and I'll write 82 here. So 82 is equal to something times 18 plus a remainder of something else. Anybody know what those numbers are?
It goes in 4 times.
Yeah, that's right. It's 4 again.
And then the
Turns out
remainder is 10.
Yeah, great, excellent. So that's true. So let me give some names to these things, and I'm going to be using the same terminology as the book. So this is a remainder. But as we go through this process, all numbers that show up in this process are going to be remainders, except for the first two. But we just think of them as remainders anyway. So I'm going to call this R0. I'm going to call this R1. I'm going to call this R2. And then in this next line here, this is still R1. The names don't change. And this is still R2. And now we've introduced a new thing, R3. So what
like linked to each other?
Yeah, they are. So the GCD of A and B is the same thing as the GCD of, okay, so the GCD of A and B, that's what we want to figure out, is the same thing as the GCD, just in different notation as of R0 and R1. So that's just different symbols for the same numbers. Now this is the same as the GCD of R1 and R2. And why is that true? That's because just in different terminology, this is the same as the GCD of B and A mod B. Okay, so we spent a long time proving this equality here. But this is going to be true from line to line. So now we've got R3, and we can bump things over one more time. Now I'll write 18 here equals blank times 10 plus a new remainder. Now everybody should be able to guess these numbers. What is this one? How many times is, Yeah, exactly. 10 goes into 18 one time with a remainder of?
8.
Yeah, 8, that's right. And so this is still R2, and this is still R3, and now this is going to be R4. So this is, we keep, because it was true for the first recurrence, you know, it's true for every recurrence for the same reason. So this is the same thing as the GCD of R2 and R3, which is also going to be the GCD of R4 and R5 when we get there. So let's keep going.
Can you keep
Anybody?
going?
Yeah, we're
Just
gonna keep.
infinitely.
I'll tell you when to quit. So we just keep going. Going to come to the bottom of the page soon. So 10 is equal to blank times 8 plus a certain remainder. So this is 1 and this is 2, right? And now we clunk one more time. 8 is equal to blank times 2 plus 0. This is 4. Okay. All right, so let me go back and assign names to the things that we just wrote down. So this one is still R3. This one is still R4. This one is R5. And let's just call 0, 0. Okay, 0 is kind of R6, I guess. So that's when things get interesting, is when, so it's also true that this is equal to the GCD of R5 and 0. Eventually you come to 0. Things just come out evenly. So this one goes into that one an even number of times. So everything is a divisor of 0. So the greatest common divisor of some positive integer in 0 is always just that, R5.
That's where it
So,
stops.
yeah, exactly. So it stops when you get to 0. And
Yep.
so the GCD here is 2. All right.
It's kind of like in discrete how we would divide a number, just keep dividing, and that's how you get the binary, like whether or not there was a remainder. You just keep going until you get to 0.
I'm not sure exactly, but yeah, it does sound like some kind of recursive division process, which is just what we're talking about right now. Okay, so what we want is we've just done the Euclidean algorithm. Now we want to use this basic setup to help us do the extended Euclidean algorithm. In the extended Euclidean algorithm, you have to come up with these numbers S and T that give you the linear combination also. So there's an easy way to do that here. So let me erase this stuff. I'm gonna need a bigger eraser. Oh, that's not an eraser. How do I make the eraser bigger? I don't know. Oh no. So I'm just gonna scratch it out.
Oh. It's probably an undo feature.
Yeah, there is. That's true. I don't remember if that's the last thing I wrote, but you're right. I probably could have pressed Control Z a bunch of times. Okay. All right. So notice that in this notation, R0 is just A and R1 is just B. Those are the two numbers that we want to find the GCD of. So you can express R2 in terms of A and B. It's easy. Can you do that? So R2 is 18. So if I just take 82 and move it over to the other side of the equal sign, then I get R2 is equal to R0 minus 4 times R1. Okay. All right. So maybe you're wondering what the point is, but hopefully you agree that that's true. So what we're going to do is we're going to keep doing this until we get down, like if we can keep going until we get to R5. R5 is the actual GCD. So what we'll do is we'll just keep expressing these remainders in terms of in terms of the previous remainders, which then let us get down to R0 and R1, which are A and B. Let's go, let's go one step farther. So R3 is this guy. So now I can express R3 in terms of R2 and R1 if I just move this over to the other side of the equal sign. So R3 is equal to R1 minus 4 times R2. So I eventually want to get back down to a linear expression just in terms of R0 and R1, but I have that for R2, so I can make a substitution and go back down. So this is the same thing as R1 minus 4 times R0 minus 4 times R1. Okay. And now I feel like I'm losing people probably, but maybe that's the good thing about having this be recorded. So this is minus 4 R0 plus 16 R1 equals 17 R1 minus 4 R0. Okay, so that's R3. Okay, so the plan is just to keep doing this until I get down to R5. R5 is the GCD, and then I will have solved the extended Euclidean algorithm problem, right? You agree? Because the game is to express 2 in terms of R1 and R0. So if you can do that, then you win. We're gonna succeed. We just have to be a little bit patient and keep going level by level. So the next level is R4. So R4 is equal to, you can just take this and shove it over to the other side. So R4 is equal to, you tell me, what should I write here? In terms of R2 and R3, what is R4?
R2 minus R3.
That's right. That's exactly right. So R4 is R2 minus R3. Okay. So now I have R4 in terms of R2 and R3, but I really want it in terms of R0 and R1, but I can do that because I have R3 in terms of those and
R2.
Yeah, so so R2 is R0 minus 4 R1, and here's R3, we just did that. So it's minus 17 R1 plus 4 R0. And the minus switched to a plus because we're doing quantity minus. And I just put these together, and this gives me 5 R0 minus 21 R1. Okay. Okay, and now it's time to do R5, which is the actual answer. So R5, take this and shove it over. So what is R5 in terms of R3 and R4? Just like
R4.
Yeah, R3 minus R4, that's right. And so now I have R4 and R3 in terms of R1 and R0. So this is going to complete the process here. So this is the same thing as, I'm probably going to need another line, so I'll just write it down here. So R3 is 17 R1 minus 4 R0. And now I'm taking away 5 R0 plus 21 R1. So this gives me 38 R1s minus 9 R0s. And I'm done. So I want to make a little space here to just sum everything up. I guess I could just zoom in, but before I change anything, because I'm going to have to erase something that's kind of important. Anybody have any questions on this whole process?
So R5 is the GCD, correct?
That's right. Yeah, R5 turned out to be the GCD. The GCD is always the last remainder that's not 0.
Yeah. Okay. Is there a term for like what R3 is or what R2 is? They're like, I know that R3 is the first remainder you get.
Uh-huh.
But just like during this process, is there something that you call those? Or...
Yeah, if you look at the algorithm in the book, it's like a recursive algorithm. So they're all kind of the same. It's like this is the initial configuration, but then you do the same thing at every stage, really. It's just like it's a recursive process.
Yeah.
So they're really just sort of three characters, which are just these three remainders. So you can call them like Ri minus 2, Ri minus 1, and Ri, I think is what the book calls them when you write the algorithm. And then I is just like the which stage of this process you're at. So we can sum it all up here. I'll write it way down here. It seems like a lowly place to write the final answer that we worked so hard for. But what we just showed is that 2, which is the GCD, is equal to 38 times R1, which is 82, minus 9 times 346. Okay, so this is the linear combination that we wanted. And that's how you do the extended Euclidean algorithm. So I'm not going to go so far as to write the pseudocode like they do in the book, because there's other things to do in life. But you can read that on your own, so that you can come up with a general formula for Ri as a function of Ri minus 1 and Ri minus 2 or whatever, that you can just sort of figure it all out in terms of constants and stuff. Something I want to point out, like what did we really need to make this whole process go? We just really needed the division theorem. So let me remind you about the division theorem. So the division theorem, it says that if you have any two numbers, what should we call these two numbers? A and B. You can write A, these are integers. So A is equal to some integer times B plus some remainder. So this is basically what made the whole thing work. And it's nice that we wrote it like this, because it exactly agrees there. So that's really all we needed, is for any integers A and B, B goes into A some number of times evenly. That's what we call Q, the quotient. And then you have a certain R, which is the remainder. Everybody learned that in 4th grade. It's funny how complicated it gets when you start introducing letters and stuff. But this is just 4th grade math. If you pick any two numbers, there's some relationship like this that you can write down. And that's really all we needed to make the extended Euclidean algorithm go. All we did is we kept moving this number over and then using the division theorem again for these two numbers. And then that gave us the third number. And then we shift things over, and then we use the division theorem again to get a fourth number, and so on and so forth. So in any kind of algebraic system where you have the division theorem, you can make the extended Euclidean algorithm go. And so what I'm kind of dancing around here is that the division theorem is also true of polynomials, because you can do polynomial long division. So it's true both for integers and for polynomials. If you pick any two polynomials, should we call these things? Maybe like t of x and s of x. Let's just let those be two polynomials. So these can just be like polynomials with integer coefficients. So there's going to be some way to write t of x equal to q of x times s of x plus r of x. And the thing that's interesting about r of x now is that the degree is going to be less than, the degree of r has got to be less than the degree of s. Okay, so now using the division theorem on polynomials instead of on integers, you can actually go through this entire process. You can do the entire extended Euclidean algorithm on polynomials also. And there's an example about that in the book, but I'm not going to do it now. Should we just do maybe the division theorem for two polynomials? I think even that is too much of a pain because we would have to do polynomial long division, and I feel like I'm brutalizing everybody already. So I think it is like way past time that we got to the point of all this. So the point of all this is to compute modular inverses. You've already seen that modular inverses are important in cryptography because we use them in our description of AES a lot. Let's go to another page. Okay, so suppose, simple example, what is the inverse of 7 mod 22? So I can answer this question. You guys remember what that means? So we want 7 times some mystery number, which maybe we can call A. It's going to be congruent to 1 mod 22. So what number is A? So the last time we considered questions like this, we really didn't have any better method than just like guess and check. But we're going to be solving equations like this for numbers that are astronomical, like 2 to the 2000th power and things like that. So guess and check does not work. But it turns out that we have a fast method of answering this question already, and it's just the extended Euclidean algorithm. So let's do it. So let's apply the extended Euclidean algorithm. Let's do XGCD. This is the way that I like to write extended Euclidean algorithm of 7 and 22. I'm going to write it the other way. It doesn't matter which one you write first, but I'm going to write it like this. Okay, so I write 22 is equal to blank times 7 plus blank. So what goes in those slots?
Is the first one 3?
3.
Yeah, 3 plus 1.
1, yeah.
Okay. And now if we were to go on to do it at second step, we would have 7 equals 7 times 1 plus 0. So the last non-zero remainder is just 1. So this means that the GCD of 22 and 7 is just 1. Okay, so from the extended Euclidean algorithm, you get some way to express 1 as a linear combination of 7 and 22. So it's easy to see what that is in this case. You can just move this one over. So we get that 1 is equal to 1 times 22 minus 3 times 7. Okay, so here's the linear combination. This is what we wanted. So now that we have this linear combination, what do? We remember the question that we want to ask is what's going on mod 22? So we take this equation and it will still be an equation, equality if I reduce everything mod 22. So I'm going to go 1 is equivalent to or congruent to, and now I'm going to reduce everything here mod 22. What happens to this one is when I reduce mod 22?
Becomes 0.
Becomes 0, yes. And so what I get is that 1 is is congruent to negative 3 times 7 mod 22. Okay, so this is what we wanted. We wanted something such that when you multiply it times 7, you get something that's congruent to 1 mod 22. And we just found that number. It turns out to be minus 3. So 7 inverse is congruent to negative 3 mod 22. And if you want a positive integer, which we do, you can just add 22 to it, which is the same thing as adding 0. And what do you get when you add 22 to -3?
19. Oh, yeah.
Yeah, that's right. So 7 inverse is 19. So you can use the extended Euclidean algorithm to solve the modular inverse problem. And because the Euclidean algorithm is so efficient, you can do this for numbers that are ridiculous. And I'm going to go do that right now. So I'm going to come back here to our CoCalc. And I made a little worksheet here. You have this too. It's in crypto activities XGCD if you want to play along here. Are you guys seeing my CoCalc screen?
Yes.
Okay, good, because there's no little green box around it. So I will open this. So here's a question. I'll make this a little bit bigger. So what is the inverse of this ridiculous number modulo this other ridiculous number? So this is a Sage worksheet, and Sage has the extended Euclidean algorithm built in. It's just the command xgcd. So I do this, and then I say, what is xgcd of these two numbers? And it returns 3 numbers. And what these are is the first number is the GCD, which is 1. We just make up 2 numbers. Usually the GCD is 1, especially if they're big numbers. And these are the Bézier coefficients. So here you can see. So D is 1, R is that, S is that. So is it true that D is equal to R times A plus S times N? Yes. And then what is the right-hand side? It's just 1. So we've succeeded in expressing the GCD as a linear combination of A and N. And what these 2 numbers are is just the coefficients that make the that are used for the expression. So now if I take the thing that gets multiplied by A and reduce it mod N, what I get is the inverse of A mod N. Here's another built-in function which gives you the modular inverse. So this is just getting the modular inverse 2 different ways. So the way you compute a modular inverse is you just do the xgcd, and so then you take the one that you want to know the inverse of, which in this case was A, and you get its Bézier coefficient, which I've called R here, and then you reduce R mod N, and what comes out is the modular inverse. So that's how you compute modular inverses, and it's going to be an important part of the RSA algorithm when we get there. So we're going to go on to a different topic now. We're going to talk about Euler's totient function, also known as the Phi function. You can read the Wikipedia article or the textbook, which is I always recommend. So let me introduce Euler's totient function back in the notebook, and then we can look at some of this Wikipedia stuff if you want to. So let's get a new page. All right. Okay. So what's the definition of Euler's Phi function? So this is the Greek letter phi, lowercase phi. You put n, where n is an integer. And what comes out is the number of numbers less than the number that have GCD 1 with respect to that number. So I'm going to write it in notation, which maybe will not be that much more clear, but then we'll give an example. So this is the cardinality of the set of integers A. So A is an integer, such that the GCD of A and N is equal to 1. Okay, so this is a set, and when you put those vertical bars around a set, you get the cardinality. So let's do an actual example real fast. So let's take 6. What is Euler Phi of 6? So let me just write, you know what, I'm going to write, I'm sorry, I meant to write Zn here. Yeah, that's right. So remember what Zn is. Zn is just the set 0, 1, 2, whoops, 3 up to n minus 1. Okay. So to figure out what Euler Phi of 6 is, let me just copy Z6 down. So 0, 1, 2, 3, 4, 5. Okay. And now we're going to cross out the ones that don't belong there. So which ones don't belong? Which numbers do not have GCD 1 with 6?
0 and 4.
0 does not, because the GCD of 0 and 6 is 6, which is not 1. What about 1? 1 is good.
Yeah, 1's good.
What about 2?
2 is good.
Yeah, 2's
Yeah.
good.
No, because the GCD of 2 and 6 is what?
Oh yeah, you're right.
It's 2, which is not
It's
1.
2.
Yeah, so 2 does not get to come. And what about 3?
3 is not good either.
Yeah, 3 is not good either, because the GCD is 3. What about 4?
The GCD will be 1.
The GCD of 4 and
Would be
6. 2, yes.
Oh, I'm sorry, it's 2, yeah.
And then 5, GCD of 6 and 5 is
1.
1. And this always happens with primes. So notice, sorry, this is I don't want to talk about that. I misspoke. Okay, so there are only 2 survivors, right? It's the same as the cardinality of the set 1 and 5, which is just 2. Okay.
So we're looking for numbers that are not greatest common denominators. They're not, or they are. Which one?
They
are
basically are the numbers that have no factors in common with 6.
Okay,
Yeah.
I
So
understand that.
let's do it again for 10. So I'll just write down 0, 1, 2. Actually, let me do a number that's a little bit bigger, and it'll be more work, but then we'll get a theorem out of it. So let me do it with 21. So phi of 21. So this is 0, 1, 2, 3. It's going to be kind of boring. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Oh, okay, great. Okay. All right. So now we're going to strike out the ones that don't belong, but I'm going to do it in kind of a systematic way this time. So you guys know that 21 is equal to 3 times 7. That's the prime factorization. So how could any of these numbers have a factor in common with 21? It has to be a factor of 3 or a factor of 7, right? Those are the only possibilities. And 0 is divisible by everything. So, but anyway, so let's write down the multiples of 3 that are in there that we have to get rid of. So the multiples of 3 that have to be eliminated are 0 is a multiple of 3 because it's 0 times 3, and 3 and 6 and 9 and 12 and 15 and 18 are all multiples of 3. And notice that there are 7 of those guys. Okay. And that makes sense because 7 times, this is 0 times 3, 1 times 3, etc. So if there was one more, then I would just have 3 times 7, which is 21, which is too big to be on the list. So that's always going to be true if some number is a product of 2 primes. So now let's look at the multiples of 7. So the multiples of 7 are 0, 7, and 14. And there's 3 of those. That had to be true because this is 0 times 7, 1 times 7, 2 times 7. If we get all the way up to 3 times 7, that would be 21, which is too big to be on the list. Okay, now let's try to figure out what phi of 21 is just by counting. This is going to be 21 minus 7, because we have to take away these 7 multiples of 3, minus 3, because we have to take away these 3 multiples of 7. But what's the problem here? We double counted 0 because 0 is on both lists. So we took away two zeros, so we have to put 1 0 back. Okay, now just observe that this is the same thing as 7 minus 1 times 3 minus 1. Okay, so you're thinking,
because you're taking out 0 in both sets.
Yeah, that's right. So we took out 0 for both sets.
Like there's 7 numbers in that set for the multiples of 3. There's 3 numbers in the set of multiples of 7. You can take out the 0.
Yeah, that's right. The 0 got taken out twice. So this plus 1 is to only take out 0 once instead of twice, because you can't really take it out twice.
Okay.
Okay, so we did all this and we found out that this is this is phi of 21. So it turns out to be 6 times 2 is 12. So that's kind of interesting. But this whole argument that we just did will always happen for any number which is a product of 2 primes. And these are the numbers that we mostly care about in public key cryptography. So if n is equal to p times q, where p and q are prime, or distinct primes, I should say, but that's too long to write. Then if I do, if I compute phi of n, then when I do that, I have to take out, what is it going to be? It's going to be n, and then I take away the p multiples of q, and then I take out the q multiples of p, and that double counted 0, so I have to put it back in. And then this is equal to p minus 1 times q minus 1. This is actually a very important formula in cryptography. Okay, so when n is equal to a product of 2 primes, then phi of n is just p minus 1 times q minus 1. And now that we have the theorem, we can do some examples of applying it. Like, what is phi of, I don't know, what is 7 times 13? It says 70 plus 21 is 91.
91,
right?
yeah.
Yeah. So I just did 7 times 13. So what is phi of 91? Let's write down p and q. So 91 is equal to this, right? So p is equal to 7 and q is equal to 13.
So it's 6 times 12.
That's right. 6 times 12, which is 72. Okay, right. Great.
Phi of 91 is 72.
Yeah, that's right. So notice that 72 is not much less than 91. So that's also kind of an important fact that I want to say more about in a second. But for now, let me just give you the general formula from the book. So it says if you have any integer n, so any integer n has a unique prime factorization. So I can write it as some prime p1 to some power e1 times a different prime p2 to some power e2 times however many prime factors it has. This is the last prime factor to some power. And so we've seen that before, but just in case that is confusing, what we're talking about here is what is the factorization of blah, blah, blah. So I hope you can see that it's pretty small. Let me make the screen bigger. I don't know, like this. Oh, stupid thing, get out of my way. But maybe you can see this. So I factored this number 1, 2, 3, 8, 9, 7, 12, and its factors are 4 2s, 1 3, and then one of these big primes. So P1 would be 2, E1 would be 4, P2 would be 3, E2 would be 1, P3 would be that number, and E3 would be 1 in the prime factorization. All right, so it looks like crazy notation, but we're not saying anything exciting here. So under this assumption, phi of n is the product. I don't know if you've ever seen this before, but for a big product, you use capital pi just the same way that you use a capital sigma for a big sum. So this is equal to pi, so this is the ith prime. I is going from 1 up to k. EI minus pi to the EI minus 1. Okay, so that's kind of, yeah, Aiden, sorry.
That's not like 3.14, like that's not real pi, right? That's just like the ith p, basically.
Yeah, like when people write capital sigma for a sum, they do that because if it's just tradition, it's kind of dumb. Sigma sounds like S, and S is for sum, and the Greek letter pi is pronounced like P, so P is for product. So,
oh, really?
yeah, so that's why they do it like that. But yeah, that's right. It's not 3.14. It's just like a.
It's the
notation.
ith p.
Yeah, it's a notation for a big product. So let's give an example. So if I do the Euler Phi of 2 squared times 3 cubed times 5, then this will be 2 squared minus 2 to the first power, which is just 2, times 3 cubed minus 3 squared times 5 to the 1 minus 5 to the 0, which is 1. And I don't know what that would all add up to, and I don't care. I just want to show how it works. Okay, that's how the formula works. So here's something to observe here. To compute, this basically means that we can compute the Euler Phi function quickly if we have a prime factorization, and it turns out to be an if and only if. So if you guys probably know by now that in cryptography you pick 2 big primes which are secret, and then you present to the world their product, and you can quickly determine the product, but from the product you can't determine the primes because factorization is a sub-exponential running time. We talked about all that last time. So it takes a very long time to factor. And this method of computing phi that we just talked about, that requires a factorization of n. You have to be able to express it in terms of a product of primes. So question is, is there any faster way to compute phi of n than factoring it? Because if not, then it seems like finding phi of n is just as hard as factoring n. And right now people think that's true. They think that there's no essentially faster way to compute phi of n than to factor n. Okay, so
Quick question, Professor.
Yeah.
So for p and q, like in a practical standpoint, like would those be our keys? Like
Yeah, that's exactly right. So P and Q are your private key. Yeah.
So each one of those is going to be like 128-bit long, like random prime number.
Even bigger, like they're going to be like, I'll show you. So let's go over to Sage now and do some examples with this too. And let's go back to, here we go. Oh, here's Euler's totient for the first few n. Notice that this is kind of chaotic, but also sort of like intriguingly regular. And
there's a method to the madness.
Exactly, but nobody knows what it is. Like figuring out exactly how this function works is extremely, extremely hard, and they're still working on it. You probably are aware of the Riemann hypothesis is the most famous unsolved math problem, and one way to understand what it's saying is it's kind of trying to understand the asymptotically how this function phi works. So,
imagine doing this without the internet.
yeah, because I mean, Euler lived a long time ago, like 310, more than 300 years ago. So, yeah, they did a lot of computation by hand. So here's an example. These are 100-bit primes, and so I'm using. Are you guys looking at this? Euler, you see Euler Phi here?
Yeah,
Okay.
We can see your Kokok.
Yeah, great. So these are 100-bit primes, but for RSA, you would use primes that are more like 1024 bits, like that. This n would just be like Padao. Yeah, and then yeah, so that's kind of too big to make the point that I wanted to make. So what I wanted to show here is these two numbers are basically the same. Like the difference between them is for how big they are. It's like a rounding error, and that's because if you look at this formula, this is equal to PQ minus P minus, all right, yeah, minus P minus Q plus 1, which is sort of like, it's like this P times Q is like n. So, and each one of these are like the square root of n. So it's like n minus the square root of n asymptotically. Square root of n is much smaller than n. So just the point I wanted to make here is if n is a big number like it will be in cryptography, then phi of n is also a huge number. Okay. So just in terms, let's go over like what's secret now. Oh, also we should talk about something else. So let me go back to the notebook. We might have to do the secrecy stuff next time. So let me give a new page here, and let me put all of the stuff that we've been talking about together. So let's look at 21. You know, this is going to be really asking you to reach back, but I want you to remember the multiplicative group mod 21. These are all the numbers between 0 and 20 that have a multiplicative inverse modulo 21. And it turns out, I think we talked about this last time, the numbers that have a multiplicative inverse mod 21 are exactly the numbers that have no factors in common with 21. So those are the numbers 1, 2, 4, 5, 8, 10, 11, 13, 16, 17, 19, and 20. Okay. So how many, what is the size of this group, multiplicative group? Here's a hint. We figured this out about 10 minutes ago in a different context.
21 minus 1.
No. These numbers have no factors in common with 21. That means their GCD with 21 is 1. So that means this is exactly phi of 21. So this is the number of sets in this multiplicative, the number of numbers in this multiplicative group is just exactly the same as the number of numbers that are relatively primed at 21, which is phi of 21, which is 7 minus 1 times 3 minus 1, which is 12. And you can count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is always true. If you look at the multiplicative group mod n, or any n, the number of elements it's going to contain is always phi of n. And this also relates all the way back to what we were doing with the extended Euclidean algorithm at the beginning of class. Like if you want to know 8 inverse mod 21, then you use the extended Euclidean algorithm to write 1 as s times 8 plus t times 21. Can anybody actually figure that out? I'm sorry, I can't figure it out. But if the GCD is 1, then you reduce both sides of this equation modulo 21 to get 1 is congruent to s times 8 mod 21. And then it turns out that 8 inverse is congruent to s, and you've solved the modular inverse problem. But what if the GCD is not 1? Then this obviously would not work because you wouldn't have 1 as congruent to the product on the right-hand side. So it turns out that in those cases where the GCD is not 1, this equation has no solution. Because if it did have a solution, then 1 would be expressible as a linear combination of 8 and 21, and the GCD of 8 and 21 is the lowest positive number that has such an expression, and so the GCD would be 1 after all. Ugh. So the take-home message here is that a number has a modular inverse mod, a multiplicative inverse mod 21 if and only if its GCD is 1. And so that's why we only include the numbers that have GCD 1 with 21 in this multiplicative group. That's not just true for 21, that's true for any n. And that's why the multiplicative group is what it is. And that's why it has the cardinality that it has, and this is how you compute inverses in that group. So that's all pretty great. So that
it's not just for 21 though, right?
No, it's not just for 21. Yeah, it's for any.
Yeah, that's just an example.
Yeah, that's right. It's for any number. So here's a good exercise for you is, why don't you try to figure out what 8 inverse is, and then if you wanted to, you could verify it using Sage, because Sage has the xGCD function and also the modular inverse function. And if you do the extended Euclidean algorithm here, you could check your answer back on the other sheet. So we have just like a few more minutes. So let me say one more thing. This is going to be kind of an informal statement. So suppose that n is equal to p times q, and n is public. This is the way it works in the cryptographic setting. So everybody gets to know n, but p and q are secret. So these are the private keys. Nobody gets to see them. So it turns out that the following are equivalent. So the following are equivalent. 1, knowing p. So suppose that you somehow figure out what p is. You know p. So if you know p, it turns out that this is really the same as knowing q. Why is that true? It's because if you know P, then Q is just equal to N divided by P, and division doesn't take that long. So if you know P,
You know it.
yeah, exactly. If you know P, you can quickly figure out Q. If you know Q, then you can quickly figure out P because P is just N divided by Q. So something that's kind of surprising is that this is also equivalent to knowing phi of n. So we've already argued that well, we haven't really made an argument. I just said that people believe that figuring out phi of n is just as hard as factoring n. But we can kind of give like a little bit of argumentation now. We can show how if you know P, okay, so suppose you know P, then you know Q, then you can figure out phi of n because phi of n is just equal to P minus 1 times Q minus 1. Okay, so that means 1 implies 2 implies 3. Okay, everybody agree? Because if we know P, then we know Q, and if you know P and Q, then you know phi of n. Now the question is, can we bring it back around like this? So the question now is, if you know phi of n, how is it that you figure out P? So let's argue for that. So suppose that phi of n is known. So suppose we know n and phi of n, and we want to know P. So I can write down a couple of equations. I can write down the equation phi of n is equal to P minus 1 times Q minus 1. And I can also write down the equation n is equal to P times Q. So both of those are true statements. Now, in this ugly orange color, I'm going to circle all the known terms. That's known, and that's known. So the only unknowns here are P and Q. So I have two independent equations and 2 unknowns. So can you solve that? Yeah, it's not that hard. So you can, this is 2 equations and 2 unknowns can be solved. And if we had more time, we could do it. Let me just get you started here. So you would do Q is equal to P over N. Doesn't matter which way you, sorry, Q is equal to N over P. And then you can substitute that in to this other equation. And then you get phi of N is equal to P minus 1 times N over P minus 1. So now you have 1 equation and 1 unknown. So the only unknown here is P. Man, that's just vomitous color. And so you can solve that. It's just like solving a quadratic equation, basically. Okay, so anyway, the message is these things have to be are equivalently secret in cryptography. Knowing P, knowing Q, and knowing phi of n. That's a good place to stop. Anybody have any questions?
I have a quick question. Like the point of it isn't to have it be impossible. It's to have the right people have access. So like unless you know the private keys, you won't be able to find you won't be able to find in. Right? Because it's not just trying to make it so big that nobody can do it. It's trying to make it so that only if you have access, like if you're authorized and you know what the private keys are, that you can get the correct answer.
Yeah, so the big picture is we're going to give everybody this number n, and then everybody can use n to encrypt messages to us. But the only way you can decrypt those messages is by knowing P and Q. And so we want everybody to be able to encrypt messages, but only people who know P and Q to be able to decrypt messages. And we want it to be kind of functionally true that the only way they can know P and Q is for us to tell them. But in theory, if they had like, you know, some alien computer or something, they could factor in, like a quantum computer, for example.
Very hard to do.
Yeah, exactly. Unless you have
Like,
a quantum computer, and then you can do it.
Impossible.
Yeah, it's kind of practically impossible without a quantum computer. Okay. So today is the 26th. And I'm going to go back to this other picture here. And you can see, oh, 23 people ended up showing up.
Always here, Professor.
Okay, what are you guys seeing right now? My stupid face?
No, seeing you.
That's what I said.
He was complimenting you.
No, oh, I'm not saying stupid.
Oh, it's the, here's what I want is the chat window. Okay.
Yes.
Oh man. Okay. Yeah. Right. Oh, not the chat window. I don't like the way this looks. I'm gonna stop the recording now because this is gonna be dead boring, and I'm gonna take attendance.